Have you ever wondered if a high-dimensional universe exists around us, invisible to our eyes? Imagine a world where life has advanced technology, able to send signals through time. This concept, popularized by the movie Interstellar and represented visually as Calabicus, is more than just a fascinating idea. It's a theory that has captured the attention of scientists and enthusiasts alike. But the question remains, does a high-dimensional universe really exist? And if so, why do scientists believe it can coexist with our universe? Let's travel back in time to 1907, when a 28-year-old Einstein proposed a groundbreaking theory. Einstein, then a second-tier technician at the patent office, believed that massive bodies like the Sun cause a distortion in space. It's not that the Earth revolves around the Sun, it's actually continuously falling in the curved space created by the Sun. This was a revolutionary idea. Einstein redefined gravity as the way an object distorts the space-time around it. This theory was a radical departure from the traditional understanding of gravity. It shifted our perspective, painting a picture of a universe where space is not an empty stage, but an active participant, bending and shaping under the weight of celestial bodies. This was not just a new definition of gravity, it was a new understanding of the universe itself. Einstein's theory was a game changer, but it was just the beginning. Fast forward to 1919, when mathematician Theodore Kaluza took Einstein's theory one step further. This was a time when the world was still grappling with the groundbreaking theory of relativity, but Caluzha, a keen observer and ardent fan of Einstein, dared to dream bigger. He pondered over the implications of adding another dimension to Einstein's three dimensions of space and time. This was no ordinary proposition. Caluzha was suggesting a four-dimensional universe. Now, what happens when you add this extra dimension? Caluzha found something remarkable. By applying the mathematical formula of general relativity to this expanded four-dimensional space, he derived not just gravity, but another formula. This was the formula used by scientists to describe the electromagnetic force. What Caluzha had managed to do was unify these two forces in a single equation. This was a monumental step towards a unified theory. When Caluzha shared his research with Einstein, the great physicist was initially perplexed. This extra dimension was a novel concept, but Einstein's intuition sensed the potential in this theory. After 2 years of contemplation, he finally endorsed the publication of Caluzha's paper by the Prussian Academy. Caluzha's theory, while seemingly fanciful, was a leap into the unknown. It was a daring proposition that added a whole new dimension to our understanding of the universe. It was a step closer to the elusive dream of a unified theory, and a testament to the boundless possibilities of human imagination. Caluzha's theory, while seemingly fanciful, added a whole new dimension to our understanding of the universe. So how can we possibly comprehend a four-dimensional universe? Well, let's take a step back and consider a three-dimensional cube. If we were to deconstruct this cube, we could create a representation of it on a two-dimensional plane. This is a process we can understand because it's within the range of our visual and cognitive experience. Now, let's try to apply this same principle to a four-dimensional cube. This is where it gets tricky, because as humans we're limited to experiencing the world in three dimensions. But if we could somehow deconstruct a four-dimensional cube, we'd end up with a projection in our familiar three-dimensional world. This projection, although not a complete representation, gives us an inkling of what a four-dimensional universe might look like. While the existence of a high-dimensional universe remains a theory, it's a theory that stretches the boundaries of our understanding and challenges us to see beyond what our eyes can perceive. Scene script: can you conceive of a world where the fundamental building blocks are not particles but strings? Welcome to the realm of string theory. Imagine a universe where the bedrock of all matter, the fundamental constituents of everything that exists, are not tiny particles, but microscopic strings. Strings that are in a perpetual state of vibration, oscillating in different patterns and rhythms. This is the essence of string theory, a groundbreaking concept that began to take shape in the late 1960s. In our tale of discovery, the protagonist is physicist Nanbu Yoichiro. While pondering over an equation used by Italian physicist Veneziano to describe elementary particles, he stumbled upon something extraordinary. A revelation that would forever change our understanding of the universe. He discerned that the particle states represented in the equation were not just simple particles, but vibrating strings. This was a pivotal moment, the birth of string theory. It was not a deliberate invention, but rather an unexpected revelation that emerged out of the blue. For the first time, the most basic structure in the universe was defined: strings. These strings come in two varieties, open and closed, and their continuous oscillations form the basic particles of matter. These basic particles then band together to form atoms, and atoms combine through chemical reactions to form molecules. These molecules make up the world as we know it, from the air we breathe, the food we eat, to the very cells that make up our bodies. Even we, ourselves, are composed of countless strings. However, these strings are so minuscule that they elude detection by any scientific method known to mankind. Yet scientists speculate that in a cross-section of an extremely small space, these strings are neatly arranged together. Each string vibrates differently, and their paths depict a multitude of behaviors. Before the emergence of string theory, no one could have imagined that the foundation of our world would actually look like this. This unexpected discovery turned our understanding of the universe upside down, but the journey of string theory was only just beginning. But every great theory faces its hurdles, and string theory was no exception. The path to understanding the universe's most fundamental structure was paved with challenges. Physicists and mathematicians hit a snag when they discovered tachyons in their equations. These hypothetical particles, zipping through the cosmos faster than light, were a conundrum. After all, nothing in our universe is supposed to travel faster than light. Enter the German scholar Caluzha, who had once been a lone voice in the scientific wilderness. Years before, he had proposed a radical solution to such problems: increase the dimensions. At the time, this idea might have seemed like a leap into the unknown, yet as string theory wrestled with the enigma of tachyons, Kaluzha's unconventional approach suddenly appeared in a new light. Fast forward to the 1970s, and we find physicist Claude Lovelace taking up the dimensional baton. Lovelace embarked on a journey not through space, but through dimensions. He gradually increased the dimensions in his equations from 3 to 4 to 5. And then, in a moment of startling revelation, he pushed beyond to 26 dimensions, and lo and behold, the tachyons vanished from the equation. This unexpected result was as baffling as it was exciting. The scientific community was set abuzz. Physicists followed Lovelace's lead, delving deeper into the dimensional rabbit hole. Their investigations led to the discovery of superstrings, a new kind of string that could exist in 10 dimensions. With superstrings, string theory found a solid mathematical footing. It was a moment of profound beauty, where the abstract world of mathematics and the tangible universe seemed to align perfectly. String theory, once an unfathomable concept, has given us a new lens to view the universe. Its tale reminds us that the pursuit of knowledge is filled with twists, turns, and unexpected revelations. So, what strings of knowledge will we uncover next in our quest to understand the universe? It's a question that has puzzled philosophers and scientists for centuries. The cosmos, with its boundless depths and unfathomable mysteries, invites us to explore, to learn, to question. At the heart of this cosmic puzzle is the Big Bang, the explosive event that birthed our universe some 13.82 billion years ago. In its infancy, our universe was a 10-dimensional realm, a symphony of space and time vibrating in perfect harmony. But as the universe cooled, this delicate balance faltered. The 10-dimensional universe split into two separate entities. A 4-dimensional universe, our familiar realm of length, width, height and time, and a 6-dimensional universe, a microscopic world, ever collapsing, so tiny it eludes our observation. Yet these two universes have always coexisted, inseparable twins in the cosmic dance. In the vastness of space and time, a man named Edward Witten dared to redefine our world. In the spring of 1995, at the University of Southern California, a revolution was about to unfold. Edward Witten, a physicist of no small renown, stepped onto a stage to deliver a lecture that would shake the very foundations of physics. His topic? String theory. But Witten wasn't merely rehashing old concepts. He presented a daring synthesis, combining not one, not two, but 5 different superstring theories. The academic world quaked as Witten's words echoed through lecture halls and laboratories. His audacious blend of theories, previously considered distinct, challenged the status quo, pushing the boundaries of our understanding of reality. Scholars and enthusiasts alike scrambled to grasp the implications, quickly dubbing this the second revolution of superstring theory. But why a revolution? Because Witten didn't merely add to the discourse, he transformed it. His work redefined our understanding of the universe, its origins, and its fundamental structure. This wasn't just a revolution, this was an evolution of understanding, a leap towards the profound mysteries of the universe. Witten called his unified theory of superstrings the M theory, a theory that would redefine our understanding of the universe. In merging the 5 superstring theories, M theory allowed for the first grand unification in human history, bringing together 2 of the 20th century's greatest theories, quantum theory and general relativity. This was a leap that not only redefined our understanding of the universe, but also opened up new, profound questions. The M theory proposes the existence of higher dimensional life forms whose intelligence could far surpass ours. Just like in the movie Interstellar, these beings might manipulate time, enabling the past to perceive the future. They could even use black holes as bridges to traverse space. But what happens when all strings resonate in harmony? As we stand on the brink of understanding, we are left to ponder. When all strings resonate, will the universe merge again to become 10-dimensional? Is that the beginning of the universe or the end? Is it the onset of a grand history or the advent of the Dark Ages?